Hello, everyone. Welcome to this week's meeting for recovery. Today is April 29th, and here's an overview of what we're going to be going over this week. So we're going to start, of course, with the stuff we did last week, and then the majority of this presentation is going to be over the ground test and how it went. I really want to emphasize what happened during the ground test. So it's the only topic we're going to cover today. And then lastly, we're going to talk about what we're going to do this upcoming week. So, well, there's supposed to be more pictures here. I guess it's loading. Let me know if the connection is decent, by the way. I am sitting outside of the Nook. So let me know if the Wi-Fi is not working, and I can maybe try to move inside and get a table in there. Anyhow, so last week we finished the calculations part of the black powder and CO2 calculator. So previously we were using a pressure-based approach instead of a force-based approach. So whenever we try using different parameters from the examples provided in the instructions, we were not able to get the same results. So we kind of worked our way with the ideal gas law and pretty much derive the way we need to do it for our approach. And that seems to be working. And the cool thing about this calculator is that if we know the geometry and the gas properties of the gas we're using, yes.
You cut off from.
Okay, hold on. Let me just get another table then.
Did he cut up for you guys again?
It kicked me out of the meeting. Okay, let's try again. And hope it doesn't happen. If it does, I'm going to go inside of the Nook and see if I can find a table. He's not able to find a table inside, so let's try again. Okay, what was the last thing y'all heard? All right, I'll just
yeah, I like yeah. Like you, as soon as the slide loaded, that's when you cut off.
Really? So y'all missed this whole slide? Damn. Oh my.
Most of it for me.
Okay. All right, let me go see if I can find a table inside. I'm gonna pause the recording. All right. Okay, so I'll just restart. We had some technical difficulties there, but from last week, we finished working on the calculations part of the calculator for the black powder and CO2 charges. So previously we were using a pressure-based approach for the actual equations, but we're trying to have a pressure force-based calculator. So basically what we did is we worked our way back using the ideal gas law. So what the calculator essentially does, it takes a force input and then it calculates the pressure on the cross-sectional area that's perpendicular to the direction we want to apply the force. So in our case, since we want to eject in a direction perpendicular to the cross-section of the rocket, that's the area where the force is going to be applied. So that's how we get our pressure value And from that, we use the material properties of the gas, and using the ideal gas law and the geometry of the rocket, we can calculate exactly how much black powder or CO2 we need to have to generate a specific force. So I think this time we are I feel confident in the results that we got. However, since it's a force-based calculator, I couldn't find something similar online. So the way we can validate our results is by essentially making a pressure-based calculator from the work that we have so far. And if it aligns with what the online calculators give us, then we know that our results are good to go. Then the other thing we did on Wednesday was the ground test, which is what I'm going to discuss in the next section, sorry. Okay, so the ground test. So the ground test was meant to test the CO2 and black powder charges, including the upper airframe, the nose cone, the avionics tray, and shear pins. So we were using 3 440 shear pins requiring 120 pounds of force to break. Last semester, when we were designing and making all of these decisions, we settled on a 1.5 time force multiplier to ensure that the shear pins would always break. So we aim to produce 180 pounds of force. So this left after breaking the shear pins, theoretically there would be 60 pounds of force on the nose cone that would keep it, that would push it. So the procedure and the methodology, you can find more information about it in the testing procedure document, which is the link right here. But essentially what we did is we assembled the CO2 system and the black powder system. Then we place the assembled systems on the bulkhead. And then once avionics assembled the avionics tray, we put the bulkhead on, and we put the avionics tray inside the avionics bay with the assembled bulkhead. And then we put the avionics bay inside of the airframe, which is this picture here. You can see there the avionics tray is inside of this bay here, and then we have the bulkhead there. And then once that was inside, we put the nose cone inside and we put the shear pins. And then the last part of the test was to trigger it remotely. So for the CO2, we used a 12-gram cartridge, which you can see the 2 different ways that we calculated which one to use. The first one was by using the instructions manual. So 6-inch airframe, and then if we were to make the volume of the nose cone or of the entire recovery bay into a cylinder, it would be, let's see right here, 19.17 inches. So that would put us like between 12 grams to 16 grams. We decided to use 12 grams because half of this would be 20 and we're slightly under that. So we decided to use 12 grams. And then the other way we decided to use that was by using our calculator. So we put the gas properties for CO2 here and then the force value we're trying to generate. And the result was 7.56 grams of CO2. So you go to the closest CO2 cartridge size to, that there is to whatever value we get from this, which is 12 grams. So the assembly for the CO2 system was mostly unproblematic. The only issue that I think we did have that we need to work on is we were not able to get the E-match tip to be flush with the electric match with the igniter holder here. As you can see here, it was sticking out a little bit. And then whenever we did have the test, the black powder piston inside the CD3 did go off, but the CO2 cartridge was never punctured. So the CO2 never came out and we weren't able to break the shear pins. So the potential failure points for this is either that we did not thread in completely the CO2 canister. Whenever we took it apart after it failed, I unthreaded the CD3 on the bulkhead a little bit, but not all the way. And then Gustavo, a few moments later, barely touched it and it just came off, which to me seems like we did not thread in the CO2 cartridge all the way. It's also possible, since the igniter was not flush, maybe that led to failure. I know that when I took off the CD3 and I was trying to clean it up, there was a lot of residue inside, which maybe part of it was unburned black powder. So that could have been another possibility. And then what I think is most likely is that the thickness of the bulkhead prevents the piston that punctures the CO2 cartridge was not able to reach it, because it hit the bulkhead and it wasn't able to reach the CO2 cartridge. So that's something that we'll probably have to test next week. And I hope that's the case, because last time we tested it during the ground test, everything was the same except for the fact that the E-match was not flush this time. But I don't think how that would lead to it failing. So the analysis for this is, like I said, making sure that the piston can reach the CO2 canister. Maybe we need to check if there's any issues with the threads and on the canister that we use and the CD3. We definitely need to practice the assembly procedures. I think the reason why the E-match was not flush with the holder is because whenever we were packing the wadding paper, we did not leave enough room for us to pull the E-match. So I think the best way that we could eliminate a lot of these is by having another test where it's just the bulkhead and the CD3. I would talk to the sub-team leads to see if we can set that up maybe next week while we wait for the new nose cone to get delivered, so we can keep on testing. But I feel like we should check in the lab first. And if we see that it can't reach, maybe expand the hole a little bit. And then on Wednesday, we conduct another ground test to see if it works. And then for the black powder, this is where things kind of took a turn. So for the black powder system, we use 1.8 grams of black powder. Like I said, this was determined from the calculator. You see here 180 pounds of force using the gas properties for black powder and the volume of the recovery bay. We got a value of 1.78. So the assembly for the black powder charges was ideal. There were no issues with it, especially since they were pre-assembled during the lab. All we had to do was connect them to the terminal. Some observations from the test. I will play the video in a bit, but the charge was significantly more powerful than expected. I forgot to include a video of a ground test that we did 2 years ago, where it was the same basic layout. So we just attached the nose cone to the upper airframe and then attached the shear pins. And for that one, we used 1.6 grams of black powder. And it was not as powerful as the one we conducted. So I guess now it's the best time to play the video. So I'm just gonna mute myself and I'm gonna play it real quick. So as you can tell from the video, not only was the explosion really loud, but it ended up traveling way further than what anybody was expecting. And then it hit the wall here of the house. And unfortunately, the nose cone kind of took it pretty hard and we destroyed the nose cone. I think overall there was a lot of oversights that we should have accounted for, but the most important were the clearance and the line of fire of the nose cone. Um, I don't know how we did not consider that we were aiming it right at the house. I think another one is that we should have had a preventative collision method in case the nose cone did travel too far. In this case, there was nothing to stop the nose cone if it went too far. Another big one is the projectile motion of the nose cone, considering the mass, force, and the launch angle. That's a really simple thing to calculate, but we didn't. And another really important one is that instead of starting small and moving our way up to our force value, we went all in the first trial, which was not the brightest idea. At the end of the day, what we're trying to test here was if we could break the shear pins or not. So maybe we could have started with a value that should theoretically not break the shear pins, so like, I don't know, 80 pounds, and then move to 120 pounds to see if it breaks, and then maybe 140 pounds. Instead, we went all in. We went with 180 pounds of force, which was not a good idea. So the consequences, as I said, the nose cone was damaged beyond repair, but lucky for us, there was nobody in the way, so nobody was able to get hurt. But this could have had the potential to harm someone. Black powder is no joke, and there's a reason why we stayed really far away from it. And the team had to scramble to find a new nose cone. Lucky for us, I think the purchase order was put in today, and we should be able to get it by Friday, which is great news. But if that wasn't the case, we could have placed the team in a really bad situation. So there is a lot of necessary changes that I think we need to make to the ground test. Number one is have a minimum clearance distance of 50 feet in the line of fire. I think any separation distance above 50 feet is unnecessary. If we have a separation distance greater than 50 feet, then the shock cords are not going to be that long. So whenever the shock cords reach their full length, they're going to have to take all that force and absorb it because they have to decelerate the nose cone traveling really fast. So definitely a clearance of 50 feet, I think is an excellent idea. The next one is having some sort of collision prevention method after the 50 feet. So this could be something like a soccer net or a blanket to catch the nose cone if it goes further than that distance. Another one is to have a sufficiently long cord to prevent any component traveling too far. Another one should be that we should probably cap the maximum amount of force at 1.5 times the separation force. I think anything more than that is unnecessary and a safety concern just by looking at the video. And then this I already kind of mentioned, but we should probably scale up to our goal separation force. Like I said, we could probably start small, around 80 pounds, and then move up to the force that it takes to break the shear pins. And once we do that, we have successfully completed or we've obtained the results that we were aiming to look for. I think another factor I think is that the only reason why we wouldn't cap the separation distance is if we're trying to somehow validate the calculations that we've made. So we know the velocity of the nose cone is traveling, the launch angle and all that. We probably calculate exactly how much force was on the nose cone when it got ejected. But still, if it's traveling more than 50 feet, it's probably way too much force on the nose cone. So yes, I think getting an estimation of where the rocket's going to land, or where the nose cone or whatever component is going to land, by doing the projectile motion calculations is something that we should do from now on. And this is something that we can easily add to our calculator. Um, so if we know the mass of the nose cone, the launch angle, and the theoretical force that should be on the nose cone, once the shear pins are broken, we can get an estimate of how far the nose cone can go. And if it's over 50 feet, then we probably want to decrease our amount of black powder or CO2. I think another thing to consider is that since all the pressure goes on the nose cone, especially for these where we don't have any recovery component, we should probably minimize our launch angle. Like I said, for these tests, we're interested in knowing if the shear pins break. So we're not really that interested in our separation velocity and distance. So it's okay if a lot of the energy of the nose cone is absorbed by the ground due to a really low launch angle. I think that's okay because those 60 pound of force, I think all of us didn't expect them to launch the rocket so fast. And we did a really, we really overlooked the fact that we were aiming the rocket at a really high angle. I think it was probably really close to like 45 degrees, which is why it travels so high and so far. And then another thing that we didn't do right before we triggered the ejection was get a verbal confirmation from everyone. I think that's really important. And from now on, if you have any concerns, especially before we're about to activate um, the ejection charges, please speak up, no matter if you think it's a small concern or a critical, especially if you think it's a critical one, please say something. Engineering relies on peers revising each other's work and decisions. That's engineering basically. So please, if you have any concerns during a ground test, please let us know. Um, and then the figures here, these are a more detailed version of the bullet points that can be found in the procedures document in the results section. So please, I strongly recommend that all of you take a look at it and give it a read. There was also some less critical issues and improvements to be made. One of them was that the U-bolt threads were too long. And this caused the avionics tray to hit it. And there is a simple solution to this. We can either add a nut on top of the U-bolt and keep the ones underneath to move the threads up a little bit. Or alternatively, we could cut more threads off, but that kind of took a little bit more work. So if the nut method works, I think we should just do that. We also have to make sure that whenever we connect the wires to the terminal block, we connect it to the right one. I don't think it was our mistake, but definitely something that we have to be aware of because we were not able to test it the first time because we attached it to the wrong screws. And another thing I want to mention is whenever we do attach the wires to the terminal block, we want to make sure that we twist the ends of the wire clockwise on the top of the screw and move our way down. So as the screw is turned and screwed into the terminal, it pretty much sandwiches the wire in between threads. Another thing that we observed was that the central axis of the CD3 and the CO2 was not perfectly straight. As you can see by this picture here, it's kind of hard to see, but this should be straight, but it wasn't. And I think it was coming into contact with the screw. So this could be another reason why the CD3 did not work this time. And then another minor thing we can improve on is memorizing which holes on the airframe are for the screws or rivets and which are the relief holes. I think that's a really simple thing to learn, so I'm not too worried about that one. And moving on to upcoming, I think on Monday, our biggest priority is to determine what caused the CD3 to fail, as well as cleaning it up after use. And then I did talk to Analysis about handing off the calculators to them, because I think there is some like interface changes that could be made so the calculator is more efficient and easier to use. So I want to make sure that we provide them some sort of explanation of how the calculators work. So I'll be following up with y'all to see what the progress on that is like. And then if we have time on Wednesday, if there's no ground test, I think we should really start practicing holding the parachutes and the cords and putting it inside of the airframe. Is there any questions? I know that was a lot, but please, if you have any questions, ask away.
I have a question.
Yes.
Is there an estimated date by which you would like Analysis to complete the calculator interface?
Is there a date for when we want this done? Is that your question?
Yeah, for when you want us to like finish working with the calculator.
Oh, I don't think we have a deadline. I think right now, I mean, we can use the calculator, but there's no rush. I think Analysis is free to take as much time as they need. Any other questions? All right. I know today was a little serious, and that's because, well, we did some mistakes during the ground test, and I want to make sure they're not repeated again. So I wanted to take my time with y'all and make sure that all of you who are going to be here next year and years after that, make sure that y'all don't repeat the same mistakes that we did during this ground test. So I really wanted to emphasize the changes that needed to be made and emphasize on the mistakes that we did so y'all can learn. I will see y'all next week. Good luck with your exams, and y'all got this. We're almost there. Just a couple more weeks left. I'm always here if y'all need help or have any questions. So yeah, have a great weekend, y'all.
You do.
Bye. Thank you.
They say